So see, other day we learned about preparation reactions. Now let me quickly go through chemical reactions. And alkyl halides and aryl halides, if you compare, most of the alkyl halides we have already learned it as a part of reaction mechanism, isn't it? Especially chemical reactions we have already gone through, except for some Grignard reagents, which I'll be discussing that. Now let me quickly take you through chemical reactions here, starting with first one. You see, first one is about oxygen-sided nucleophiles, which means when you have oxygen-ended nucleophiles, where oxygen O minus or OH is going and attacking the alkyl halide. So let's see the reactions here. If you have any alkyl halide like this, which is 1 degree, okay, then that when you react with NaOH, it will often go via SN2 mechanism to give alcohols and NaX. This is the reaction which you expect. Got it? This will be via SN2 mechanism. Because it is at 1 degree position, usually we expect it at SN2 mechanism. While if we had a 2 degree alkyl halide and that if you react with NaOH, this will also favor via SN2 to give this as 2 degree alcohols and NaX. But at the same time, some amount of SN1 is also noticeable, which means this one can undergo formation of carbocation, and because it is in an aqueous solution, water can also attack to give you an alcohol part. So that's why both SN1 and SN2 reactions are favorable when it comes to 2 degree alcohols. Okay. Third one is when you have 3 degree alkyl halide reacting with aqueous KOH or NaOH. This will give you more alkene via E2 mechanism and some alcohol via SN1 mechanism. Okay, the SN1 mechanism here is because you will have a carbocation forming first, and on that carbocation H2O will be attacking and thus giving you a 3 degree alcohol. This is via SN1. But because you have a 3 degree chloride, SN2 is not possible directly. So via E2 mechanism, it will give you an alkene formation. This is with reaction with NaOH. Okay. So what is important thing to note here is on heating, E2 is always greater than SN1. Okay. Second, B, if you notice, if you have alkyl halide with Ag2O moist, Ag2O moist will also offer you more of SN2 type of mechanism. The reaction would go something like this here, where Ag2O is becoming 2Ag plus and O2 minus, and O2 minus with H2O will become 2 moles of OH minus. So it is in a way same as this above reaction, where OH minus is going attacking here, X minus is leaving, and you'll get this as 1 degree alcohol. Got it? Next, check out next reaction here, C, where alkyl halide plus H2O is giving alcohol plus HX via SN2 mechanism. If water has to react on this primary position, it's very weak. As a nucleophile, it's very weak and it cannot form a carbocation. So directly water attacking X minus leaving is difficult. But if only some heat is provided, then it will go towards SN2 type of mechanism and create a 1 degree alcohol. Without heat, this reaction will not happen. Okay. Next, in case if you have 2 degree, alkyl halide, that when you add it with water, it will go via SN1 mechanism to give 2 degree alcohol and HX. Got it. Similarly, if you have 3 degree alcohol, the 3 degree alkyl halide with water gives SN1 and 3 degree alcohol and HX. So you can see the last two reactions are mostly via SN1 mechanism. Okay. And if at all we have 2 degree or 3 degree alcohols plus water, but if you add it in the presence of AgNO3, then you will get alcohol as well, but most importantly, you will get a precipitate. Here, This can be used to test 2 degree and 3 degree because these will have stable carbocation cases. Okay, this will have stable carbocation cases. In fact, we should also note one important point here is, okay, adding AgNO2 increases the rate of reaction because adding the minute you add AgNO3, this Ag plus will take X minus faster and that will generate the carbocation faster. Okay, so that's how you will see only if you have water, most of the time SN1 is favorable, but only if you have primary position, then SN2 is favorable. Okay, next. Check out the D reaction here. Williamson ether synthesis. Williamson's ether synthesis when an alkyl halide react with alkoxide to give ether and RX. Okay. What do we do? Usually we take an alcohol like this and react with sodium, and that will give you alkoxide RO minus Na plus. Okay, plus half H2. So this alkoxide is to be added to the alkyl halide in an ether solution. Okay, sorry, in an aprotic solution, any aprotic solution. In that case, Rx will attack on RO, sorry, RO minus will attack on Rx, remove this X and get this form. And this is usually favored via SN2 mechanism. Okay, this is usually favored via SN2 mechanism. Got it? So, which means if it has to be SN2, this Rx has to be something called SN2 ready. SN2 ready means what? See, R can be either 1 degree, sterically unhindered 2 degree, and SN2 ready cases. Okay. SN2 ready cases, what are the SN2 ready cases? It could be either an allyl like this, an allyl halide. It could be a benzyl halide. It could be like this, a double bonded O's with halogen here like this. These are highly favorable SN2 cases. So CH3 1 degree alkyl halide, CH3X 1 degree alkyl halide, and very less hindered 2 degree alkyl halide like this. So only these kind of alkyl halides will be able to react in the above reaction. This is what happens with Williamson ether synthesis. Clear everybody? And see these examples here one by one. So starting with first one, see here, in case if you have a simple ethyl bromide reacting with ethoxide, correct? So this will via SN2 give you uh, dimethyl ether and alkene. Okay, and you know that because it is highly SN2 favorable, so this will be major. But at the same time, ethoxide is a very strong base. Because of its strong base character, it can take H plus from here, relieve Br, and makes an product like this via E2 mechanism. So that means this is via SN2, this is via E2 mechanism. Feel good? See the next example. This is the first example. See the second example. Okay, if you have 2 degree bromide ethoxide and this on reaction with, I can get this as a E2 SN2 product, and this could be E2 product. Okay, now this is going via SN2, this is going via E2. Here it's very difficult to say which one is major. Okay, unless heat is provided. The minute heat is provided here, if heat is provided, this will be major. If heat is not given, this could be major. Okay, so unless heat is provided, we cannot clearly say which one is major here. Okay. See the third case now. Third case is if you have a tertiary alkyl bromide reacting with ethoxide, now we will get an alkene which is coming out via E2, and we have an ether which is coming out via SN2. Okay. But here we can definitely say that SN2 is minor because ETO minus attacking on this position, taking away BR minus is very, very difficult form. So SN2 will hardly happen there. So here major product will be only via E2 mechanism. Okay. Next, see the fourth case. In case if you have 1 degree bromide like this, and then you have ATO minus, even this crowding will make more of alkene as major and ether as minor. So this is via E2, this is via SN2. Even this level of crowding, if it is present on the beta position, so in that case, you will not be able to see any substitution as major product. Got it? So please check the cases 1, 2, 3, 4 quickly. Next, let's see the fifth case here. So in case if you have tert butoxide treating with methyl bromide here, so this will give us, SN2 product like this, and that is the only product you can get because E2 is not possible on this position. So 100% you'll get only SN2 product here. Next, notice the sixth one. If you have a tert butoxide and you have ethyl bromide, then you will start getting E2 product and SN2 product. But E2 product will be major. This E2 product will be major, because we have learned it all earlier that this third butoxide is a very strong base and a poor nucleophile. So as a nucleophile, because of its bulkiness, it's weaker, but it is a very strong base. Hence, it will always offer more elimination than substitution. Correct? So this happens to go via E2 elimination, and this will happen via SN2 product. Okay, and now notice this. In case if you have to identify reactants to correct reactants to follow the ethers, that means which reactants can give ethers if you compare. So see, for example, if you have this ether given, what is the best thing to make this ether here? You should have this alkoxide and this alkyl halide, because you know that this is a vinylic position. On vinylic position, you cannot keep a halogen and expect this to go via SN2 mechanism. Okay, so therefore, that won't happen if you take a vinylic position. So therefore, it has to be vinyl oxide, okay, and 2 degree alkyl halide. Second, notice in case if you have one side vinyl, one side simple 1 degree. In that case, again, vinyl oxide, okay, and 1 degree alkyl halide. Vinyl with, this is allyl and 1 degree. Between allyl and 1 degree, the best reaction is when you take uh, ethoxide and then allyl halide, because allyl halide has highly favoring SN2 mechanism. And here we will have 2 degree versus allyl. 2 degree versus allyl. So again, you take 2 degree alkoxide, you take this as 2 degree alkoxide, and here you can take this as allyl halide. Okay. Next reaction, if you see, if you have methyl phenyl ether. Methyl phenyl ether, best way to go is you take phenoxide and then attack on methyl halide. Okay. Next, if you have phenyl with propyl isopropyl phenyl ether, so you can see phenoxide and isopropyl halide. Okay. Next, tert butoxide and phenyl. This is not possible at all because neither of the combinations will give you SN2 reaction. Okay. Next, phenyl on other end we have allyl. So allyl is definitely possible. So phenoxide and allyl halide. Okay. Next, if you have phenyl and this is benzyl, sorry, benzyl oxide and ethyl on the other side. So then it is, ethoxide and benzyl halide, because benzyl halides are highly favoring SN2 mechanism. And next here, benzyl with vinyl. So again, vinoxide with benzyl halide. Similarly, benzyl halide and other side we have phenyl. So we have phenoxide and benzyl halide. Next, benzyl halide and bridge position. So bridge position oxy and benzyl halide. So these combinations will give you correct ether formations. So you would be given this kind of reactants, right? All of these reactants. You need to figure out what is the best combination which can give you product of ethers. Clear? This is a very standard question. So please check this out. Next. Next is about intramolecular Williamson synthesis. Okay. Within the molecule, suppose I have an alcoholic form as well as chloride here and react with sodium. So sodium will make this as an alkoxide and chlorine is present. So internally the attack would happen from here to here. Chlorine will be removed and that will give us epoxide and Cl minus. Got it? And of course H2 is also released here, half of H2. Okay. Now the same can be done in basic medium also. That is, if you have an halogen here and alcohol on the other side with KOH, first you will get alkoxide internally, and internally the attack will take place from here to here. And as soon as the attack take place, you can get this as ether and Cl minus. This is via intramolecular ether synthesis. Okay. See, just to remind you, when you have to make these cases, right? If you want to make this best combination of ether cases, you should keep reminding yourself what is the rate of SN2 reaction. Okay. So when it comes to rate of SN2 reaction, first thing you should check out is these cases. Okay. Keto chlorides. Okay. Adjacent on beta position, you have an aldehyde or a keto position. That will be the most reactive one. Then we have benzyl halides. Okay. Chlorides or any halogen here. So let me write down this as the halogen instead of chloride only, like this. And then we have CH3X, and slightly CH3X will be lesser than allyl. And after that you have primary, and then we have secondary, then we have tertiary. Okay. So this is the typical order you should follow while writing for SN2. Okay. Right. Next, see the reaction with Ag2O. When it comes to Ag2O, you can see uh, 2 moles of alkyl halide plus Ag2O will give you ROR. Okay. If it is dry means what? We have basically Ag2O. Think in an ionic form as 2Ag plus O2 minus. And here Rx is reacting with O2 minus. So this will attack, sorry, O2 minus will attack on R. This X minus will relieve. So that will become RO minus plus X minus. And RO minus will attack on the second mole of Rx. And that's how you will get this as ROR. Okay. That is how we get this as ether. Okay. Next, reaction with alcohol. So you can see if you have 3-degree alkyl halide, react with alcohol, then you will get this as an ether plus HX. But here the mechanism is via SN1. See, SN1 mechanisms are not considered as Williamson ether synthesis. Williamson ether synthesis. So which means if it is Williamson ether synthesis, we expect this to happen via alkoxide, and through alkoxide formation, this is the product we should get. Clear? Next, you can see uh, sulfur-based nucleophilic reactions. So that means if sulfur is ending the nucleophilic form, Then what are the reactions that take place? Check first. A alkyl halide plus NaSH in the presence by SN2 mechanism, you will get this as RSH and NaX. Simple. Here the attack of SH minus and removal of X plus happens simultaneously. Therefore, it is an SN2 mechanism. Got it? Now, how do we remember these cases, everybody? So, remember like this: 1 degree, 2 degree usually use SN2, 3 degree would usually use E2 and SNO. If heat is provided, then E2. If heat is not given, go for SNO. Second, if you have alkyl halide plus R dash S minus Na plus, then you will get this as thioether. So, so these are thiols. Let me put down that thiol, and this is thioether. Got it? So we'll get the formation of thioether. Here also, how do we remember? If it is 1 degree, 2 degree SN2, 3 degree it is E2 and SN1. Okay, clear? Lastly, in case if you have alkyl halide with Na2S, then also you will get this as thioether, correct? Plus NaX. So 2 moles. You need to take this as 2 moles of Rx and you will get this same as Ag2. Here also, you can see 1 degree, 2 degree will give you SN2 and 3 degree will give you E2. Clear with the sulfur cases? Please notice that. Done. Check. Now let's see nitrogen as the ended nucleophile. Nitrogen ended nucleophiles here. So starting with first ammonolysis. Ammonolysis is a type of reaction where an alkyl halide reacts with ammonia in the presence of pyridine to give amine of different kind, 1 degree, 2 degree, 3 degree, and so you can see it is 1 degree, 2 degree, 3 degree, and 4 degree, which is quaternary ammonium salt. Okay, generally the reaction set is like this: 1 degree, 2 degree will always give you SN2, 3 degree will end up giving E2. Okay, so which means if these products has to form, it has to be usually the alkyl which is 1 degree position. Initially it should be 1 degree position. So how does the mechanism take place? Check it out. So first step is ammonia attacking on Rx. Okay, you can see this is an SN2 type to give a 1 degree first salt which will convert into a 1 degree amine plus HX. Okay, and 1 degree will become the feed for the next molecule making an SN2 attack. So you will get a salt which will convert into 2 degree amine and HX. And 2 degree becomes a feed for the next alkyl halide to get a 3 degree amine, okay, like this, and HX. And 3 degree amine becomes a feed for the next alkyl halide to get a quaternary ammonium salt. Okay, this is quaternary ammonium salt. Now all of these are SN2 steps. Every step is SN2 here. And you see all these steps are SN2 driven. Clear? And if you use excess of ammonia, primary amine will be major product. And if you use alkyl halide as in excess, then quaternary ammonium as major product. Okay, so simple reaction. If I take this as excess, then this will be major. Okay, sorry, primary will be major. If I take this as excess, then quaternary will be major. Please check it out quickly. This is ammonolysis. See the next reaction. See this example. If you have intramolecular ammonolysis, that means chlorine is chlorine and ammonia are internally present, then attack will happen internally, and you'll get this cyclic ammonium form. Okay, cyclic ammonium form is called as aziridine. Aziridine. All right. Now, another reaction of a similar kind, secondary amine, if you have it with bromine here, internally attacks will happen. You will get this six-membered ring with methyl here. Got it? So it is called as N-methyl piperidine. Okay. All right. Next, in case if you have uh, one chlorine, one bromine, but at 1,3 position with ammonia, correct? So first one ammonia will come at the most leaving group position, and from there the internal attack will take place to give this aziridine form and NaCl. Okay. And what if they are far away? If chlorines and chlorines are far away with ammonia excess, you will get on both ends of the chloride as ammonia. So this is the product formation. Okay. So see this cases, everybody. These are the type of products you should be able to figure out. Okay. So all these are the examples of ammonolysis only. Okay. So take a minute's time and go through it. This time we see if you have carbon-ended nucleophiles, if carbon end is attacking as a nucleophile. So that is alkyl halide plus triple bonded carbon that will react to give this kind of substitution product. We have seen this in alkynes also. This goes via SN2 mechanism. In case if you have 2 moles of alkyl halide reacting with R2Cu Li also, you will get 2RR. Core-Howe synthesis, we have learned this in alkanes. Similarly, we can have any vinylic uh, carbanion that reacts with Rx to give you SN2 mechanism to give this as a product, alkene as a product. Or you can have any allyl based compound that will also go via SN2, and you'll get two products, both will be 50-50 percentage. Okay. Why is that so? Because due to resonance, the attack could happen from this end also, or attack could happen from this end also. So you will get a chance of getting 50-50 percentage, considering this carbon is an isotopic carbon. Got it? This is a type of reactions you'll see it for carbon end. Next one is about reactions with AgCN and KCN. If it comes to AgCN and KCN, you will see Rx when you react with KCN will give you RCN plus RNC. For 1 degree and 2 degree, usually SN2 mechanism is favorable. This is major and this is minor. Okay, so the major one, this is called as uh, alkyl nitrile. Okay, alkyl nitrile, and this is alkyl isonitrile. Alkyl isonitrile. Got it? And lastly, if you notice, if you have 3 degree alkyl halide, it will favor E2 mechanism. 3 degree alkyl halide will favor E2 mechanism. How is this reaction proceeding? See, simple. If you have KCN, it will be K plus and C triple bond N with minus charge. So this is a nucleophile which is basically attacking on Rx. So that's how you will get this SN2 type of attack. Okay. So from nitrogen end, it will be from nitrogen end, it will be so from this end, if you notice, Rx attack, lone pair attack, and X minus will go here. So that will be minor attack. Okay. What if you have AgCN instead? So that is next reaction. If AgCN is the one which is reacting, again you will get two products, but this time isocyanide is the major product, or isonitrile is the major product. This is because AgCN, as it attacks Rx, because Ag and Cn is covalently bonded, there is no carbon anion which is present here. So it is the one which is attacking from nitrogen end only. And then you will get this as RNC and AgX. Okay. A very small proportion of AgCN will be in an ionized form, that is with Ag plus and C triple bond N minus. This is in a small quantity. So because this is in a small quantity, you would notice only cyanide as a minor product and isocyanide as the major product. Clear with this one, right? So please remember ionically bonded compounds. Now here, that is the way to remember. This is ionic bonded. So if it is ionically bonded, then cyanides will be major product. Here it is covalently bonded. So if it is covalently bonded, then isocyanates will be major product. And that is the same type of reaction you will also notice in the next case, where you are reacting with AgNO2 and KNO2. So see, if you have Rx plus NaNO2, you will get RON double bond O, and this will be major, which is alkyl nitrile, and this will be minor, which is nitroalkane. So nitroalkane is the major product. Okay. Similarly, if you notice alkyl halide plus AgNO2, you can see RNO2 plus RONO2. Here this is major and this is minor. Why? Same logic. Here also this is ionically bonded. Ionic bonded. Okay. So basically it is Na plus and O minus connected with N double bond O like this. So the attack would be more favorable for oxygen end. While in AgNO2, this is covalently bonded. This is covalent bonded. So you would typically notice the attack like this, where you have Ag connected with O and N double bond O. So only lone pair on nitrogen is more available. So the attack happens mostly from nitrogen side. Okay. So whether it is ionic bonded or covalent bonded, one thing is for sure, if it is 1 degree, you will get SN2. If it is 2 degree and 3 degree, you will usually get SN1. Okay, there is no elimination that will happen. It will often go for SN1, SN1 reaction. Clear? So I guess this part is understood, everybody. Please go through it once quickly. Reactions of AgCN, KCN, AgNO2 and KNO2. Now the next reaction we need to learn is about Grignard's reagent. Okay. So see, this is about Grignard's reagent. Clear? Preparation wise, Grignard's reagent is simple. You take any alkyl halide, react with magnesium in the presence of dry ether, you will get RMGX. Okay, so you'll get this as RMGX. Now, RMGX basically exists as RMGX dot 2 moles of that ethyl form. That is like a complex here. You can see this is the kind of complex that it forms. Another thing you need to note is that RMGX is not a free anion, carb anion. It's not a free carb anion. It's a strong base and strong nucleophile, but not a complete carb anion. So it is like in a complex form like this. Got it? And see, when it comes to RMGX, clear? So first thing you need to learn is that RMGX can be formed by 1 degree, 2 degree, 3 degree, allyl, vinyl, benzyl, phenyl, etc. They all will form 1 degree, they all will form Grignard's reagent. Okay. So if you have vinyl chloride with Mg in the presence of ether, you will get this as RMGX, vinyl RMGX. If it is phenyl, you will get this as phenyl RMGX. If you have only fluoride, correct, that will not give any RMGX, which makes us realize that the rate of formation of Grignard's reagent mainly depends upon the bond breaking of alkyl halide. So because Ri is more easy to break compared to RBr and RCl, the reaction will more happen in this direction. Got it? So any other cases where you have 1 degree, 2 degree, 3 degree, they all can form Grignard's reagent easily. Got it? And notice next point. Generally, Grignard's reagent cannot be prepared from compounds which have an acidic hydrogen. Suppose if it is already having an acidic hydrogen, it will not make the Grignard's reagent or will not keep the Grignard's reagent stable. There is some internal shifting will happen. Let me show you case by case. So first case is, if you have an halogen, on the other end we have alcohol, and this, if at all I react with magnesium and ether, first the Grignard's reagent will form, and thereafter intramolecular proton transfer will take place and will get into this form. That means there will be movement of this minus charge to take this H plus. It will take away that H plus because internally the H plus, which is more acidic, will shift there. So H will come here, minus charge will shift here, and MgX will be appeared here. So instead of staying it like a Grignard's reagent, it will now stay like this alkoxide form. Okay. Same second reaction. See, in case if you have halogen, on other end we have acid, and then you are reacting with magnesium and ether. First you will get this form, and then intramolecular proton transfer will take place. Hydrogen will be shifted, and you will get CO minus MgX plus. Okay. Third reaction, check out if you have the cyclohexyl with chlorine, and then you have a C triple bond CH, that on reaction with magnesium and ether will give you MgCl and this, correct? And intramolecular proton transfer will take place to form into this position. C triple bond C minus MgX plus. This is a product formation. One more example. See, if you have bromine on one side, NH2 on the other side, magnesium and ether. So you will get this as hydrogen shifted and NH2 minus and MgBr. So it follows first step to come here. Second step, the hydrogen will shift here. Got it? So remember, when you have an alkyl halide, along with that, there should not be any acidic hydrogen. So that brings to us a note that which all cases I should consider, because this is an amine. Amine in basic in nature, then how are you expecting this to give H plus? The hydrogen which is connected to highly electronegative elements, they all will be acting as sufficiently acidic hydrogens. And that's what I'm writing. That's what you need to learn it as a note here. That is, in case if you have OH, COOH, SO3H, NH2, NHR, amide, primary, secondary amide, alkyne, okay, thioalcohol, phenol, or even this, cyclopentadienyl, and then we have diketones like this. Got it? Diketones here, or you have squaric acid like this, right? So they all going to be the compounds which facilitate intramolecular proton transfer. They all will give you intramolecular proton transfer. Got it? Now you know that except for allyl, vinyl, benzyl, and alkyl halides, right? The hydrogen present on these positions will not give that, but rest all will give you intramolecular proton transfer, which means, suppose, just as an example, let me write down that. Suppose I have X here and CH3 here, okay? And then I'm treating this with magnesium and ether. I'm expecting that first you will get this as MgX here with CH3 here, and then I'm expecting some intramolecular proton transfer IMPT by making this into H here and CH2 minus and MgBr plus. This will not happen. So in this side, this reaction will not happen. This will not take place. Correct? So just keep that in mind. This reaction won't take place. So it will only stop at Grignard's reagent. So you cannot expect an allylic hydrogen, vinylic hydrogen, benzylic hydrogen, or any alkyl hydrogen to replace the position of a Grignard's carbon. Okay. So I'm sure you have come across these cases before. So In fact, if you have anything like a molecule, right, like this, if you have any simple molecule like this here, let's say if you have a molecule like this where you have OH here and NH2 here and C triple bond CH here and CH3 here like this, and then we have SO3H here, and this, if at all I react with CH3 MgBr, if you recall, a Grignard's reagent can pull hydrogen from all these positions. So it can pull the H plus from all these positions, and then you'll get this as O minus, NH minus, C triple bond C minus, SO3 minus, but not from CH3. So that makes to have 4 moles of CH4 coming out of Grignard's reagent. So you know that which of them are more acidic here. Okay, clear? This is the main role of Grignard's reagent. Now notice, in case if you have RMGX, that cannot be prepared from 1,2 or 1,3 dihalides as well. Which means if you have, let's say like this, 1,2 uh, dibromides here. Just a second. So in case if you have Br and Br here, correct? So because of those two bromines, right? So you will be able to see with magnesium and ether, you'll only get alkene instead. Okay, so how does the mechanism occur? Like this. So first, magnesium will try to provide the electrons to bromine here, right? And that will push the electrons here, and further Br will be pushing the electrons. So on doing that, you will see alkene is forming and MgBr2 will be forming. Done. So that's how the reaction will take place in this case. This is about 1, 2. Okay. Even if you have 1, 3 also, see, if you have 1, 3 here with magnesium and ether, you will get this cyclization. Same logic. If you have 1, 4 onwards, then the attack will not be observed. So then it will remain a stable Grignard's reagent. So 1, 2, 1, 3, you should always convert them into this respective cyclo propane group or an alkane group. Right. So remember, these are only cases observed for 1, 2 and 1, 3 dihalides. Okay. And now notice what are all the chemical reactions that happens with Grignard's reagent. So check out first chemical reactions of Grignard's reagent. First one, foremost one is nucleophilic addition reaction. That is, if you have RCOOH, then RMGX has been treated. Okay. Then we will get this as an adduct first. Adding an water or making hydrolysis will convert into alcohol. Mechanism wise, if you notice, this is what the first step is. Check out this case, how the step is. So first you have lone pair on oxygen attacking on MgX and breaking one bond of RMGX here. So this R minus will again connect to the second mole of RMGX, and this R minus will go attack here, and pi bond from here will shift onto oxygen. Like this will shift onto oxygen. So in short, if you notice, it is like a six-membered ring here. Okay. So how does that six-membered ring look like? Like this. So this is the six-membered transition state. So check it out. This is the six-membered transition state. So where we have oxygen, MgX, R, MgX, R dash, and carbon. They will be involved into this six-membered cyclic transition state, and that will give you the moment so that we can get this RO MgX plus, RO minus and MgX plus R dash MgX. Okay. And now the second step is once you get this OMGX on hydrolysis, you will get this as an alcohol. Got it? This type of an addition is called as nucleophilic addition reaction. Reason being, the first step itself is the rate determining step or slow step, where a nucleophile is attacking. A nucleophile adding on to C double bond O will make the reaction slower. So that's why this is called as the first. And the O minus Mg we are forming, this is called an adduct. Adduct is a thick solution, okay, which on hydrolysis will finally convert into an alcohol form, right? AN wording, this AN will go and will keep using this wording a lot of times. This means it is nucleophilic addition. AN means addition of a nucleophile. Got it. So please check. You have reaction as if you have formaldehyde reacting with CH3 NgBr, first you'll get this adduct, and that on hydrolysis will give you alcohol. What type of an alcohol you are getting? 1 degree alcohol. So you can see we'll get this as 1 degree alcohol. Similarly, if you have if you have acetaldehyde reacting with CH3 NgBr, you will get an adduct first that on hydrolysis will give you 2 degree alcohol. So you'll end up getting this as 2 degree alcohol. Okay. Likewise, if you have a ketone and that when you react with CH3 NgBr, it will convert into this adduct form, and then on hydrolysis, it will convert into a 3 degree alcohol and MgBr and OH. So here let me write down H3O plus. Okay. So if you want to generate 1 degree alcohol, you can use formaldehyde. 2 degree alcohol, acetaldehyde. 3 degree alcohol, you can use ketones. So ketones usually will give this reaction. Okay. Next, in case if you have uh, epoxides given, let's say like this, an epoxide is given, simple epoxide, then CH3 MgBr will make an SN2 attack. You will get this as an adduct form that on hydrolysis will give you this alcohol form. So what is the type of alcohol you are getting? 1 degree alcohol. Similarly, if an adduct with ethyl substitution is there and then you are attacking with the CH3 MgBr, this also happens via SN2 mechanism. So bond will break here like this. Here also bond breaks. So as the bond breaks here, you will see the product would be like this, an adduct that on hydrolysis will give you an alcohol which is 2 degree. Likewise, if you have one more substitution here, this way, and CH3 MgBr, that will give you this adduct, and that on hydrolysis will give you tertiary alcohol. Okay, so that is MgBr plus here. The attack is starting from this position to here. Bond is breaking on this position here. Right. So this is about 3 degree alcohols. So 1 degree, 2 degree, 3 degree alcohols can also be achieved from these various epoxides. Okay. So I would suggest quickly go through it once. What is the mechanism? What happens to the nucleophilic addition cases? If there is any doubt, you can let me know. Up to this, whatever we have learned is about nucleophilic addition reactions. Now, what you will see a new type of mechanism, which is nucleophilic substitution reaction. Okay. So let me write down that. This would be nucleophilic substitution reactions. Okay. This reaction is also called as AN-DN type reactions, which means first addition of nucleophile followed by deletion of nucleophile Okay. Another terminology that is used is SNTD, which means nucleophilic substitution via tetrahedral intermediate. Okay. Okay. Or you can also write this as SNAE, which means nucleophilic nucleophilic substitution with addition and elimination kind. Addition and elimination kind. All of them meant the same thing. Okay. So this is all about nucleophilic substitution, everybody. Now, let's see where are these reactions being more useful, or how do we make these reactions. So first, starting with first reaction with acid chloride, R C double bond O Cl. So let's see how does the reaction work here. So first it will be Rc double bond OCl plus R dash Mgx. This would give us Rc uh, double bond O R dash. Let's see the mechanism here. Mechanism is Rc double bond OCl reacted with R dash Mgx. So this R dash will attack here. The pi bond will be pushed here. So in that case, we will have this as Rc. This will become O minus, taking Mgx plus. This is R dash and Cl. So this is an AN reaction, which means addition of nucleophile. And usually addition of nucleophile is the rate determining step. And now this negative charge will try to push the electrons and see whichever is the best leaving group. Here, chlorine is a good leaving group. So that will follow to make this reaction into RC double bond O R dash plus Cl minus. So what is this reaction now? This is deletion of nucleophile. Okay. And you can see here when the nucleophile is added, it is added on an sp2 carbon, and the intermediate which has developed is sp3 carbon. Hence, it is also called as SN-TD formation, SN-TD form. And overall reaction is also called as SNAE, addition and elimination form of nucleophilic reaction. So up to this reaction formation, right, with the one step, you are making an addition of the nucleophile, then deleting an addition, deleting the nucleophile, and eventually you will getting this as the ketonic form. Okay, this is the reaction which you will get. But now listen, if you had this is one equivalent only, first equivalent. What if you have a second equivalent? So that we will continue as the next reaction here. So because it is a ketone, and you know that ketones can make reaction, this is R dash, ketones can make further reaction with Grignard's reagent, that is R dash Mgx. Now this time it is only nucleophilic addition reaction. So that we have already seen it as a mechanism. So you will get this as O minus R dash and R dash Mgx plus, and thereafter you will make an hydrolysis, and that will give us RCOH R dash and R dash. So we will get this as 3-degree alcohol. We will get this as 3-degree alcohol form. Got it? So two equivalents. So this is the second equivalent. So second equivalent. So second equivalent, which means if you have two equivalents, we end up getting into an alcohol form. Okay. This is with acid chloride. Correct? First reaction will be with first reaction is SNAE or ANDN. Second reaction is only ANDN. So eventually, after that, when you do hydrolysis, you'll get this alcohol form. Okay. Similar type of reaction you will notice happening with esters also. So now with esters, R C double bond O O. Let's say some ET here. So if you have some ethyl ester here. So what is the reaction that will happen? RC double bond O OET. Let's say I'm treating with CH3 MgBr, and this is first equivalent. In that case, you will get this as RCO minus MgX plus OET and CH3 added to it. And then OET will come out as the better leaving group here, and you will get this as a ketone with ETO minus MgBr plus. Okay. And now the second equivalent, because if you have sufficient equivalents, the second reaction will also take place. And then you will end up getting this as RCO minus MgBr plus with CH3 and one more CH3. So this is the second equivalent, and that on hydrolysis. Now notice this on hydrolysis will give you a 3-degree alcohol again. So here also same reaction, we require 2 moles. In fact, this, because this ethoxide is present, that also undergoes hydrolysis to give you ethanol. So two alcohols will be formed. One is a 3-degree alcohol, one is the ethanol which is coming from the alkyl group of ester. So I suppose this reaction is also clear how it happens with esters. Okay. So wherever you see esters, first you check out how many moles are provided. If only one equivalent or 1 mole is provided, you will stop the answer at ketone. If 2 moles are provided, then hydrolysis is given. That means you'll go all the way up to alcohols. So the third reaction, this is with acid anhydride, with anhydrides. If you treat this with anhydrates, what is the reaction? You have R, C double bond O, O, C double bond O. Let's say I have CH3 here, and that on reaction with CH3 MgBr of 1 equivalent. So what is the product you will get? So first one, you will get this as R, C double bond O, CH3. Okay. Sorry, let me put this also as R. Otherwise, it will confuse us as which side to attack. Okay. So then I'll get this as RC double bond of CH3 plus the other compound will be RCO minus MgBr plus is the first equivalent. And again you get a ketone here. This ketone when you react with CH3 MgBr, right? So you will get this adduct RO minus MgBr plus with CH3 and CH3, and that on hydrolysis will convert into an alcohol, that is RCOH, CH3 and CH3. So you will get this as 3-degree alcohol. Okay, but at the same time you notice that this acid form is also present, that on hydrolysis will remain as acid only. So which means I'll get this as RCOOH. So you will be providing these two as the products. Okay. Okay. So this is about acid anhydrides. Hmm. Okay. So next one is reaction with cyanides. Okay. RCN, right? So with this, with cyanides or with nitriles, with cyanides or nitriles. So see the reaction, what will happen? RC triple bond N. Okay. This, if you react with CH3 MgBr, so First, you will get this as RCCH3 double bond N minus MgBr plus. This is a type of attack which you will get. And now is the interesting one. So for the first equivalent, this is first equivalent. If I add the second equivalent, so CH3 MgBr here with second equivalent, okay, then the attack of this nucleophile here on carbon will be unsuccessful. Reason being, for CH3 minus to attack, this carbon should have delta positive charge. Whereas, because of this carbon having negative charge, it is not donating group. This R is donating group. This CH3 is donating group. So there is nobody who is polarizing the carbon with a positive charge. So since it does not have any positive charge, no matter how many moles of CH3 MgBr you push it, further reaction will not happen. So since that next reaction will not happen, what do we end up with? You have CH3 and double bond N minus MgBr plus. This is where it will halt, and then after hydrolysis, the first thing what you will get is RCH3 double bond NH. This is called imines. And imines are highly unstable in aqueous solutions. They are highly unstable in acidic aqueous solutions. They'll convert into this keto form and nitrogen ends up forming NH4 plus. Okay. So let me show you that this is unstable in aqueous solutions. So that's why it will end up forming a ketone again. Clear? Which means if the reaction is given like this, everybody, suppose I have given pH CH2 C triple bond N, and then I said I'm treating this with CH3 MgBr, correct? This is the example which I'm taking. And I'm saying that I'm taking this in excess. And after that, I'm following this with H3O plus. Then what is the product you will report? C. You will report this as RCH2, then C double bond OCH3 plus NH4 plus. And listen, one more thing. Because you have this in excess, this CH3 MgBr which is remaining after one equivalent is gone, rest all CH3 MgBr is remaining. That CH3 MgBr will react with water to give large quantity of methane gas. So that will become CH4. And what is remaining? Mg, Br and OH will be remaining. Done. So this is the product. Ketone is the product that you will report. So if it is cyanides, generally it will always end up at ketones. I guess this part is clear. Next. With fifth one, if you have with amides, with amides, what is the type of reaction that happens with amides? You see, RC double bond O NH2. If you treat with CH3 MgBr, see, as long as this hydrogen is present on nitrogen, that is sufficiently acidic. So hence, you will only get this as an acid-base reaction. That is NH minus MgBr plus and CH4. While if you have an completely R substituted, let's say CH3 and CH3, at that case you will see nucleophilic addition reaction will take place. So in this case nucleophilic addition will take place. So now you will get this as RCO minus MgBr plus and then CH3 with N, methyl groups here Me and Me is present, and this will try to convert into a double bond leaving this group. So first you will get a ketone RC double bond O CH3 plus N Me twice with minus and MgBr plus. And this ketone will further get reaction with second equivalent of CH3 MgBr, CH3 MgBr. So you will get the adduct as O minus MgBr plus CH3 and CH3. And then on hydrolysis, it will convert into a tertiary alcohol. And this nitrogen containing compounds will convert into a secondary amine. H3O plus, it will become Me twice NH, which is 2-degree amine. So 2-degree amine and alcohol, these are the products you will report. So this is very similar to that of acid chloride. So you can see acid chloride, acid anhydride, amides, they all will have very, very similar reaction. Got it? They all will have very, very similar reaction here. Clear? Now, generally, reactivity order, if you compare, okay, reactivity order of RMGX, okay, it will be most reactive towards aldehydes of this kind, simple aldehydes, like this. Then we have CH3CHO. Then we have PHCHO. Then we will have ketones. Then we'll have more bulkier ketones like this. Then we have phenyl type of ketones like this. This is first type of reactivity order you should know. The second reactivity order is when you are comparing an aldehyde compared to that of ketone and compared to that of acid chloride compared to that of anhydride, C double bond OR anhydride, and compared to that of ester and compared to that of amide, that is NR2. This one. This is the second order you should know. So how anhydrides, acid chlorides, they are all reactive towards RMGX. Okay, so it's very simple here. Addition reactions are most favorable, so that's why first additions are happening. And within addition, you can see the one which has least crowded and high delta positive charge. That is the most effective one. So which means what are the factors you are checking out here? High delta positive charge and less steric hindrance. These two are the main factors in the first case. Second case is only high delta positive charge. So whichever has high delta positive charge, that will always going to be highly favored. So you can see chlorine is withdrawing, so it will have high delta positive. OC is slightly donating, this is more donating, and NR2 is highly donating. So that's how the order will be. Clear? So right, okay, quickly go, mainly check out cyanides and amides, everybody. Rest all are very easy ones or similar ones. Okay, please check this out quickly. A standard example that is asked in this case is this one, which is very commonly asked. We have studied this before in benzene. That is, if you have chlorobenzene and you're reacting with Mg in the presence of ether, first you will get a Grignard's reagent minus and MgBr plus, and then if you react this with carbon dioxide or call it as dry ice, okay, sorry, one minute. That is the second reaction I would like you to learn. First learn this reaction, okay. That is if you react with HC double bond O N Me twice, okay, this one first and followed by hydrolysis. So then what do we get? We know that first a nucleophilic addition will happen, okay, and thereafter second time also it will get added. Sorry, NH2 will go away here. So if at all I take only one equivalent, let's say I took only one equivalent here. So if I take only one equivalent, I will get this as C double bond OH plus NHMe twice. Correct? Suppose in the same question, if at all I take two equivalents, H C double bond O N M E twice. And if I take two equivalents followed by hydrolysis. So in that case, I might end up getting this as C OH and then another benzene ring here with NHMe twice. Okay. So if one equivalent, you'll end up at benzaldehyde, two equivalent, you'll end up at this alcoholic form. Okay. I guess the reaction is clear. Now see the sixth reaction. Sixth reaction is with dry ice or carbon dioxide. Okay. So if you react RMgX with CO2, right? So you will end up, and followed by hydrolysis, you will end up getting an acid RCOH. So see the mechanism. How does it take place? So here we have R dash Mg R minus and Mgbx plus reacting with C double bond O double bond O. So this minus would go attack on this carbon, right? Just like a nucleophilic addition here. So this is the same nucleophilic addition. RC double bond O and O minus MgBr plus. Furthermore, no more moles of RMGX will attack. So then on hydrolysis, it will convert into an acid. So simple. So wherever you have an acid group, so you will convert this into the same thing. Now let me just copy the same reaction which I wrote here. So then I just need to change that reagent here. So take this as another example. So in this example, so instead of taking uh, this compound here, now I'll take carbon dioxide and hydrolysis. Okay. So if you have this reagent as carbon dioxide followed by hydrolysis, then we'll get as benzoic acid, right? And MgX and OH. Clear? This is with dry ice. See the seventh reaction with oxygen with O2 or reaction in air. How does Grignard's reagent react in air? Okay. See RMgX as you react with O2. Okay. So this will become R minus, sorry, RO O minus MgX plus, and that on reaction with hydrolysis, sorry, reaction with second mole of RMgX will convert into 2 moles of RO minus MgBr plus, and that on hydrolysis will give you 2 moles of alcohols. See, structure wise, if you notice, it is R minus almost MgX plus this kind of charge distribution, and we have O double bond O. So this RO minus will attack on the empty pi star orbital, and that pi star orbital rearranges, and R minus will attack on oxygen, and you'll get this as ROO minus and MgX plus. Okay. And once you get that here, now you know that single bonded oxygen and oxygen are highly unstable. So they are very prone to break. So RMgX as you react, this can easily connect onto this oxygen. Here the bond breaking will take place, and you will get this as 2 moles of RO minus and MgX plus, and that followed by hydrolysis is what will give us 2 moles of alcohols. Okay. So simple mechanism. So if you react with air, you will get this product. Okay. Next reaction is with, ethyl orthoformate. ethyl ortho format. So if at all I have RMGX reacting with HCOAT, OET and OET, this is called ethyl format, right? So this would happen, first step is going to happen via typical SN2 mechanism, where this R minus will try to attack on sp3 carbon, relieving one OAT. So that will make it as RCH with OET and OET. Okay. Now attacking on the second mole becomes very, very challenging. That will not give you successful yield. That means if you have RMGX again, try to attack here. Now this will not give a lot of yield of any product. So instead, now if you try directly hydrolyze it, this will convert into a ketonic form and 2 moles of ethanol will be formed. 2 moles of ethanol will be formed here. So if you want to get this into an aldehyde form like this, then you can use it on ethyl ortho format and you'll get this product. I guess this is clear, everyone. Yeah. Now, usually when you make the preparation of Grignard's reagent, what is a mechanism that goes through? See, mechanism of RMGX preparation. Mechanism of RMGX preparation. So check out. If you have Rx and react this with Mg, so you will get this as R RMGX here, correct? In the presence of ether. This is the overall reaction. So basically, how this is happening is, first, magnesium is trying to release its electrons. This is step one. So this will become R dot and MgX, right? MgX here. Sorry, first not R dot. Rx. First you will have this as Rx with minus charge on it and Mg with plus charge and one single radical. Okay, because this minus charge has come because of this extra electron on X. And once you get that here, now you would notice, now you will notice that this will convert into a radical form, okay, and get this as R dot plus mgx dot, because this plus and minus will convert into mgx and that single electron will remain, okay, and this R dot plus dot mgx will terminate with each other, and that's how it is making a bond as rmgx. So you can see no carb anion formation, no carb anion formation. So that's the point you need to note from this mechanism. So it usually do not make any carb anion formation. Okay. So since it is like a radical form, let me show you with this example. Suppose in case if you have Br here with a double bond like this, Br here with double bond here, and then we treat with Mg and ether. Okay. And suppose if there is an isotopic carbon here. So if this is an isotopic carbon, so what do we get here is you will get double bond with this carbon becoming from this carbon it is going to become MgBr for sure, like this, and the other product will be like this with double bond and MgBr here also. Okay, so this is that isotopic carbon. Isotopic carbon. So why does this happen? Because during the mechanism, if you remember, one radical formation will come here. So that radical formation can show resonance stabilization like this. So that MgBr will terminate on both the ends, here also and here also. You'll get these two products of Grignard's reagent. Okay. Now, usually we say usually usually rmgx plus rx reactions are not much observed unless it is allyl rmgx or benzyl rmgx. They will react with rx. Okay, in this case you will see the product formation. So here in simple rmgx you will hardly see any reactions happening, but with allyl and benzyl you will see the reaction happening with rx. Clear on that, everybody? So this is typically how the reactions will take place. Okay.